Hello, this is Richard Collins. Welcome to Cloud Formation, Unit 7 of ATM101, Weather and Climate of Alaska. This unit explores how clouds form in the Earth atmosphere and highlights the role of stability in the formation of clouds. In this unit, we will investigate the following topics: adiabatic processes in the atmosphere, dry and moist adiabatic lapse rates, lifting of air in the atmosphere, formation of clouds in the atmosphere, and the behavior of gases under the ideal gas law. This lecture supplements our textbook Weather, a Concise Introduction by Gregory Hakim and Jerome Patou with material from the textbook Meteorology Today by C. Donald Aarons. There is a conceptual error in the discussion by Hakim and Patou on how dew point temperature varies as air moves vertically in the atmosphere. I've used material from Aarons to address this. Finally, I want to make one content warning. These slides include a picture of a naked Greek scientist in a bathtub. To create a framework for studying the movement of air parcels in the atmosphere, we consider adiabatic processes. These are processes where the parcel does not exchange any energy with its environment as it travels through the atmosphere. An example is the use of a bicycle pump. When we inflate a tire, we use our own muscle energy to push the air into the tire. As the pump piston rapidly compresses the air and pushes it into the tire, we do work, and the work is converted into heat. We experience this as the pump warms. Thus, we have conservation of energy, as our mechanical energy is converted into thermal energy in the gas. In releasing air from a tire, the air rapidly travels from a high-pressure environment to a low-pressure environment. The exiting air does work by pushing the atmosphere back. The air must provide the energy for that work, and it does so by cooling and giving up thermal energy. We experience this as the exiting gas feels cold. The first law of thermodynamics is a statement that energy is conserved. Any change in thermal energy of the gas must equal the work done by the gas. And this is the equation on the left side of the figure. The change in thermal energy is given by the product of the specific heat at constant pressure, Cp, by the change in temperature, delta T. In the inflation case, delta T is positive, the temperature increases, and the work done by the gas is negative, as it is work done by the human on the gas. In the deflation case, dT is negative, as the gas cools, and the work done by the gas is positive. In the atmosphere, the pressure drops as an air parcel rises, and so the parcel must expand. This expansion means that the parcel is doing work as it pushes the atmosphere back as it rises. This expansion happens more rapidly than any heat transfer by conduction, convection, mixing, or radiation. Thus, the parcel is rising adiabatically and must provide the energy to do the work from its own resources. The only resource it has is its own internal thermal energy. Thus, the parcel cools as it rises. This is essentially how clouds form. Humid parcels of air rise, cool, and eventually the water vapor condenses and forms droplets or ice crystals. Remember, water vapor is an invisible gas, while cloud particles are visible. To understand how clouds form, we need to better understand the process of adiabatic expansion. Air rises in four basic ways. In the upper left, we show air rising by convection. The sun heats the ground, and the ground conducts that heat into the air above it. A warm bubble of hot air forms that is less dense than the air around it, and the air rises. Eventually, the air cools and falls back to the ground, and we have a convection cell. In the formation of pop-up cumulus clouds, the horizontal extent of these rising parcels of air is about 5 kilometers. In the upper right, we see lifting over topography. Topography is the geographic term for the surface features of the Earth. Wind blows air, and if it encounters a hill or a mountain, it is forced over it. This is also called orographic lift, as the geographic term for mountains is orography. Lenticular clouds often form over mountain peaks, as the wind blows over mountains, and the horizontal scale of the mountains is about 150 kilometers. In the lower left, we see that when air converges or comes together, instead of piling up, the air rises. This is how air rises in low-pressure systems, which are associated with clouds and rain. The horizontal scale of low-pressure systems is about 500 kilometers. Finally, in the lower right, when air masses meet at fronts, the cold air moves under the warm air, and clouds form in the rising, warmer air. However, the character of the clouds and precipitation that form at warm fronts and cold fronts differ significantly, and we will discuss this later in the course. Typically, the troposphere cools with altitude at about 6.5 degrees Celsius per kilometer. This environmental lapse rate is determined by the balance of radiative and convective processes. Consider a parcel rising from the surface at 1000 hectopascal to 1 kilometer at 900 hectopascal. A rising parcel of dry air cools at about 10 degrees Celsius per kilometer, while the environmental lapse rate is 6.5 degrees Celsius per kilometer. The parcel cools from 10 degrees Celsius to 0 degrees Celsius due to adiabatic expansion, while the environment is cooled from 10 degrees Celsius to 3.5 degrees Celsius. The parcel at 1 kilometer or 900 hectopascal is now colder than the environment. Similarly, a falling parcel of air will warm by 10 degrees Celsius for every kilometer it falls. So a parcel starting at the environmental temperature of 3.5 degrees Celsius at an altitude of 1 kilometer will increase in temperature to 13.5 degrees Celsius at the surface due to adiabatic compression. The environment has warmed from 3.5 degrees Celsius to 10 degrees Celsius. The parcel is now warmer than the environment at the surface. As a moist or humid parcel rises, the saturation vapor pressure ES decreases as the temperature decreases. The actual vapor pressure E also decreases as the total pressure decreases. As E decreases, the dew point temperature also decreases. On average, ES decreases more rapidly than E, and so the relative humidity rises as the ratio E over ES increases. In this example, a parcel rises from the surface at 1000 hectopascals to 1 kilometer at 900 hectopascals. In this case, the relative humidity of the parcel does not reach 100% and condensation does not occur. The temperature falls from 20 degrees Celsius to 10 degrees Celsius. The saturation vapor pressure drops from 23 hectopascals to 12 hectopascals. The actual vapor pressure falls by the same factor as the pressure, from 10 hectopascals to 9 hectopascals. The pressure has dropped by the same factor of 0.9 from 1000 hectopascals to 900 hectopascals. The dew point temperature falls from 8 degrees Celsius to 6 degrees Celsius. The relative humidity rises from 43% to 75%, where 43% represents the ratio of 10 hectopascals to 23 hectopascals, and 75% is the ratio of 9 hectopascals to 12 hectopascals. As the environmental humidity decreases rapidly with altitude, the parcel is much more humid than the environment at 1 kilometer, where the environmental relative humidity is 20%. For the parcel of air falling from 1 kilometer to the ground, the temperature increases from 13.5 degrees Celsius to 23.5 degrees Celsius. The dew point increases from -12 to -10 degrees Celsius, as the vapor pressure increases from 3 hectopascals to 3.3 hectopascals. The saturation vapor pressure increases from 13 hectopascals to 29 hectopascals, and the relative humidity drops from 20% to 10%. The relative humidity at the parcel at the surface is much lower than the environmental relative humidity of 43%. In general, the dew point temperature decreases by 2 degrees Celsius per kilometer as the air rises in the atmosphere. It falls by 2 degrees Celsius per kilometer as the air falls in the atmosphere. This compares with a dry adiabatic lapse rate of 10 degrees Celsius per kilometer. In a saturated parcel, we add an extra component of energy to the situation, the release of latent heat due to condensation. As the water moves from gas to liquid, it releases thermal energy as the molecules in the gas move more rapidly than the molecules in the liquid. The parcel now cools due to doing work expanding, the adiabatic expansion, and warms due to release of latent heat of condensation. This yields a moist adiabatic lapse rate of 6 degrees Celsius per kilometer. In this case, at saturation, the relative humidity remains 100% and the parcel loses water as it maintains a vapor pressure equal to the saturation vapor pressure. Rising from the surface at 1000 hectopascals to 1 kilometer at 900 hectopascals, the temperature drops from 17 degrees Celsius to 11 degrees Celsius. The saturation vapor pressure drops from 19 hectopascal to 13 hectopascal. The vapor pressure drops from 19 hectopascal to 13 hectopascal. The dew point temperature drops from 17 degrees Celsius to 11 degrees Celsius following the saturation vapor pressure, and the relative humidity remains constant at 100%. Again, the parcel has a higher relative humidity than the environment around it at 1 kilometer. Consider humid air that flows over a mountain. This is called orographic uplift. The parcel rises on the windward side of the mountain A parcel starting at 20 degrees Celsius with a dew point of 12 degrees Celsius rises 1 kilometer and cools to 10 degrees Celsius with a dew point also of 10 degrees Celsius. The parcel is now saturated, has a relative humidity of 100%, and condensation occurs and a cloud begins to form. Continuing to rise, the parcel continues to cool, the dew point follows the temperature, condensation continues, and the relative humidity remains at 100%. However, the parcel is now cooling at the moist adiabatic lapse rate of 6 degrees Celsius per kilometer. At the mountain peak at 3 kilometers, the cloud is at a temperature of -2 degrees Celsius, the dew point is also -2 degrees Celsius, and the relative humidity is still 100%. Passing over the peak, the parcel now falls on the leeward side of the mountain. The parcel has lost most of its water, and so the parcel warms at 10 degrees Celsius per kilometer, while the dew point increases at 2 degrees Celsius per kilometer. Falling the 3 kilometers, the temperature rises 30 degrees Celsius, while the dew point rises 6 degrees Celsius. One result of the release of latent heat is that the air warms by 8 degrees Celsius between the start and end of its mountain climb. This is an example of a chinook, where air warms as it passes over a mountain. Chinooks occurring in the Rockies were famous for melting winter snows. The word chinook comes from the Native Americans living along the Columbia River. Their name chinook became associated with the winds as well as the king salmon in the Columbia River. Chinook winds are relatively common in Alaska, where onshore flow from the Gulf of Alaska rises over the Chugach and St. Elias Mountains. The weather map shows a typical situation where a strong low-pressure system in the Gulf of Alaska, with an occluded front, drives moist winds onshore, indicated by white arrows, and snow falls mainly on the coastal regions, indicated by the blue shading on the map, with much less precipitation, if any, inland. The values of the various meteorological quantities are shown in the table. I have added the situation at half a kilometer to highlight that the parcel rises under dry adiabatic conditions for the first kilometer, shaded in orange. Once the air is saturated, the vapor pressure follows the saturation vapor pressure, and the relative humidity remains constant at 100%, shaded in blue and purple. The parcel reaches the peak, shaded in purple, with the lowest humidity, 5 hectopascals, only 36% of the 14 hectopascals it started with. The air has been effectively cold-dried. The air parcel now descends, steadily warming, increasing in vapor pressure, increasing in saturation vapor pressure, and decreasing in relative humidity. In passing over the mountain, the air has warmed from 20 degrees Celsius to 28 degrees Celsius. The humidity has fallen from 14 hectopascals to 8 hectopascals, a drop of 57%. The dew point has dropped from 12 degrees Celsius to 4 degrees Celsius, and the relative humidity has decreased from 61% to 21%. Thus, the air parcel has been transformed from colder and wetter air to warmer and drier air. This is the slide with the content I warned you about. Archimedes, one of the all-time great scientists, supposedly discovered his principle in a bathtub, exclaimed "Eureka," I have found it in Greek, as he jumped out of the bathtub and ran through the streets of Syracuse naked. Archimedes famously died while engrossed in a math problem during the Roman invasion of Syracuse, where he was killed by an unappreciative Roman soldier. Archimedes' principle is based on the idea that parcels of fluid do not fall in their own fluid. Thus, some force must exist to hold the fluid parcels up against gravity. This buoyancy force must equal the weight of the fluid in the parcel. If we replace the parcel of original fluid with a less dense fluid, the buoyancy force is now greater than the parcel weight and the parcel rises. If we replace the parcel of original fluid with a denser fluid, the buoyancy force is now less than the parcel weight and the parcel falls. So that leaves us with the question of, how do steel ships actually float? Colder fluid particles are denser than warmer fluid particles, as fluids generally expand when they are heated. So warmer air can rise while colder air can fall. Sometimes it requires a push or disturbance to get a fluid parcel on the surface to move, even if it is less dense. It is worth noting that humid air is lighter than dry air, which also helps in the formation of clouds. Water molecules are composed of 1 oxygen and 2 hydrogen atoms. Oxygen atoms have a mass of 16 atomic mass units, while hydrogen atoms have a mass of 1 atomic mass unit. Thus, a water molecule has a mass of 18 atomic mass units. In comparison, a nitrogen molecule composed of 2 nitrogen atoms has a mass of 28 atomic mass units, and the oxygen molecule has a mass of 32 atomic mass units. When a new water molecule evaporates, it displaces a heavier molecule and does not squeeze in as an extra molecule. Think of the volume of air as a bus with a limited number of seats. If a water molecule takes a seat, it pushes an oxygen or nitrogen molecule off the bus, and the bus gets lighter. Thus, a volume of humid air is lighter than a volume of dry air. So cold, dry air is denser than warm, humid air. So we are interested in the stability of the atmosphere. Will a parcel that is nudged upwards fall back down to its original position? Will it take off and keep rising indefinitely? Will it rise and stop at some higher altitude? Or will it fall back from small nudges but take off when the nudge exceeds some threshold magnitude or tipping point? These ideas are illustrated by a ball sitting in a deep valley, on a hill, on a flat surface, or in a shallow valley on this slide. Questions of stability also frame the discussion of climate change. Will our nudge of fossil carbon dioxide return to the previous climate, run away to something very different, run a short distance and stop, or can we stop before reaching a tipping point? This question is tied to the positive and negative feedbacks, if any, in the climate system. Venus is an example of a runaway climate driven by carbon dioxide. The surface temperature on Venus is higher than that on the surface of Mercury. In the atmosphere, the moist and dry adiabatic lapse rates define the stability of the atmosphere. For an atmosphere with a lapse rate less than the moist adiabatic lapse rate, 6 degrees Celsius per kilometer, the atmosphere is always stable. So any atmosphere where the temperature falls in altitude at less than 6 degrees Celsius per kilometer or rises with altitude is stable. Parcels rising in these atmospheres will become colder and denser than surrounding air and fall back to their original position. This is the blue region to the right of the blue line of the moist adiabatic rate. For an atmosphere where the lapse rate is greater than the dry adiabatic lapse rate, 10 degrees Celsius per kilometer, the atmosphere is always unstable. Parcels, both dry and moist, rising in these atmospheres will be warmer and less dense than the surrounding air and continue to rise, running away. This is the purple region to the left of the red line of the dry adiabatic rate. These are the conditions where we get deep clouds, thunderstorms, hail, and tornadoes. In the region between the two lapse rate lines, the air is conditionally stable. Parcels of moist air will rise while parcels of totally dry air will not. Thus, the stability depends on the humidity of the parcel. This is the green region between the two lapse rate lines. We have discussed in the past how the stratosphere is stable because the temperature increases with altitude. This is one of the reasons supersonic planes like to fly in the stratosphere. The air is less turbulent than the troposphere, and the planes have a smoother ride. Regions where the temperature increases with altitude are called inversions. Inversions commonly occur in Fairbanks in the winter. Under long, clear nights, the air is dry, and so the infrared radiation emitted by the ground escapes to space and the ground cools. The air at the surface then cools by conduction. However, as air is a poor conductor and there is little convection during the cold nights, the overlying air is warmer and so an inversion forms. Furthermore, to add insult to injury, Fairbanks is in a valley, and so colder, denser air in the hills sinks into the valley, adding to the chill, what I call Fairbanks brisk. I reviewed the Unit 4 data from our WTYC weather station and the corresponding Unit 5 data from the PAFI weather station at Fairbanks International Airport, FAI. PAFC sits at 135 meters above sea level. WTYC sits at 186 meters above sea level. So WTYC is 51 meters above PAFC. On the afternoon of the 29th of January, we see a 10 degrees Celsius difference between the two station temperatures, with WTYC warmer than PAFA. The radio sonde launched at FAI shows an inversion extending up to about 1,200 meters. The tropopause is about 9.5 kilometers, and there is a stratosphere with no strong inversion above that. The lack of an inversion reflects the weak ozone heating in the winter. The radio sonde shows a temperature drop of 10.2 degrees Celsius between the ground at 135 meters and an altitude of 186 meters above sea level. This is consistent with the 10 degrees Celsius difference between the airport and the campus weather stations. We now consider the development of small or fair weather cumulus clouds, cumulus. In the lowest kilometer of the atmosphere, A, the atmosphere is absolutely unstable, with an environmental lapse rate of 11 degrees Celsius per kilometer. In the second kilometer, B, the atmosphere is absolutely stable, with an environmental lapse rate of 6 degrees Celsius per kilometer and 4 degrees Celsius per kilometer. In the third kilometer, C, the atmosphere is stable as the temperature rises with altitude, giving a lapse rate of minus 6 degrees Celsius per kilometer. So a parcel of air starting at 35 degrees Celsius or 95 degrees Fahrenheit with a dew point temperature of 27 degrees Celsius or 81 degrees Fahrenheit is soon warmer than the air around it as it rises. Once it is warmer than its environment, the parcel has reached the level of free convection. The unsaturated air parcel rises, cooling at 10 degrees Celsius per kilometer, and the dew point temperature falls at 2 degrees Celsius per kilometer. The temperature line red approaches the dew point line green, and they meet at 1 kilometer. At 1 kilometer, condensation occurs, the relative humidity reaches 100%, and this marks the bottom of the cloud. Above 1 kilometer, the air parcel continues to rise at the moist adiabatic lapse rate, 6 degrees Celsius per kilometer. It remains buoyant up to 2 kilometers. At 2 kilometers, the parcel temperature and the environmental temperature are both 19 degrees Celsius. The parcel is no longer buoyant, but will continue upward for a short distance before beginning to fall. This defines the popcorn structure at the top of the cloud. The level where the condensation occurs, in this case 1 kilometers, is called the lifting condensation level. It is the altitude where the cloud base is realized. Looking at the temperature figure, can you determine how the base altitude of the cloud changes in altitude if the parcel is more or less humid to begin with at the surface? Stability influences the formation of cumulus clouds. In a stable atmosphere, small cumulus clouds, cumulus form. These clouds do not yield precipitation. If the atmosphere is conditionally unstable in the mid-troposphere, then we get more extensive clouds, cumulus congestus. Cumulus congestus may have precipitation and have turbulence that may be severe. If the atmosphere is conditionally stable over most of the troposphere, cumulonimbus clouds form. These clouds extend up to the tropopause. They flatten out in the stable stratosphere, which gives them their anvil appearance. Turbulence is severe with updrafts and downdrafts within the cloud. There are areas of heavy precipitation where raindrops may be accompanied by snowflakes, snow pellets, ice pellets, and/or hailstones. The World Meteorological Organization, WMO, maintains an extensive cloud atlas with great photos at the website shown in the slide. Wrapping up this lecture, we delve into the ideal gas law. A parcel of air has a given volume, mass, temperature, pressure, and density. Experiments have shown that for an ideal gas at fixed temperature, the pressure of the gas is inversely proportional to the volume. For an ideal gas at fixed pressure, the volume is directly proportional to the temperature. Combining these two experimental findings, we have the ideal gas law that says that the product of the pressure and volume V divided by the temperature T is a constant. If we heat a gas and raise the temperature, the product of the volume and the pressure exerted by the gas must increase. Rearranging the variables for a fixed mass of gas M and volume V, we have a density ρ, and we can express the ideal gas law as the pressure P equals the product of the density ρ, temperature T, and gas constant R. The gas constant R is specific to each gas. For dry air, it has a value of 287, where pressure is given in pascals, density is in kilograms per meter cubed, and temperature is in Kelvin. We can plug numbers into the equation and determine typical values for the density of air at the ground, given pressure and temperature. We can determine the temperature at 500 hectopascal given the density and pressure. At a pressure of 1013 hectopascal and temperature 15 degrees Celsius, air has a density of 1.226 kilograms per meter cubed. At a pressure of 500 hectopascal, if the density of air is 0.690 kilograms per meter cubed, the temperature is 252.5 Kelvin or minus 20.5 Celsius. For a parcel of air in the atmosphere, if it is neither expanding nor contracting, the inward force exerted by the environment equals the outward force exerted by the gas. The pressure is just the ratio of the force to the area over which it acts, and so if the environmental pressure equals the parcel pressure, the parcel will maintain its volume. If the parcel pressure is less than the environmental pressure, the parcel will contract. If the parcel pressure is more than the environmental pressure, the parcel will expand. The law describes a quantity of gas in equilibrium with variables that have settled down after a change. Consider what happens when the temperature of a parcel of gas is increased. Then the volume and/or the pressure exerted by the gas must increase. The volume can only increase if the pressure increases and pushes the gas outward. So initially the pressure must increase, then the volume increases. As the volume increases, the pressure must decrease, and so the expansion slows down. Eventually the parcel reaches a new equilibrium state where the volume has increased, the temperature has increased, the density has decreased, and the pressure is unchanged. The parcel can now rise in the atmosphere and form a thermal. The ideal gas law describes the natural behavior of gases as they've been observed and validated extensively over several hundred years. The law is defined in terms of macroscopic properties of bulk fluids: pressure, temperature, and density, or mass and volume. The kinetic theory of gases says that a gas is actually composed of point particles that ricochet around. The average kinetic energy of the particles is a measure of the temperature. The pressure is the average force of the particles ricocheting off the surface of the parcel, and the density of the gas is defined by the mass of the particles in the volume. We did not observe individual gas molecules directly until the 20th century, yet the kinetic theory has been accepted as it has been consistent with the behavior of gases over several hundred years. Our summary and takeaways are: dry parcels of air cool under adiabatic expansion as they rise in the atmosphere and warm under adiabatic compression as they fall. The dry air parcels cool and warm at the dry adiabatic rate of 10 degrees Celsius per kilometer. Moist parcels of air increase in relative humidity as they rise. If the moist air parcel reaches a relative humidity of 100%, condensation occurs, and the rising air parcel will cool at the moist adiabatic rate of 6 degrees Celsius per kilometer. The dew point of an unsaturated air parcel will fall by 2 degrees Celsius per kilometer as it rises. The atmosphere, like any system, can be stable, unstable, neutrally stable, or conditionally stable. The stability of the atmosphere is determined by the temperature lapse rate and its relationship to the dry and moist adiabatic lapse rates. The stability of the atmosphere determines if air will rise in the atmosphere, the type of clouds that form, and the amount and type of precipitation that falls. Temperature inversions are stable and can trap pollutants in the lowest layers of the atmosphere and impact air quality.